3.5 kilometers below the surface of the Mediterranean Sea, in water pressure that would crush a submarine, there is a string of glass spheres listening for something that has already passed through your body about 400 times while you read this sentence. On February 13th, 2023, at 16 minutes past 1 in the morning, one of those spheres caught something enormous. A single particle carrying roughly 220 million billion electron volts of energy, something like 16,000 times more energy than a single proton-proton collision inside the Large Hadron Collider, the most powerful particle accelerator humans have ever built. It remains, to this day, the most energetic neutrino any instrument on Earth has ever recorded. And when the discovery was finally confirmed and published 2 years later, in February 2025, the people who built the machine that caught it still could not tell you, with any confidence, where in the universe it came from. That gap between catching something and understanding it is where this story actually lives, and it's built on a mistake almost everyone makes about how you catch something this small. The instinct is to assume that finding a rarer, more elusive thing requires a smaller, more delicate instrument, something closer to a scalpel than a net. That instinct is exactly backwards. It has been backwards for almost a century, ever since a frustrated Austrian physicist accidentally invented this entire problem by predicting a particle he was personally certain nobody would ever see. In December 1930, a 30-year-old Wolfgang Pauli was dealing with a genuine crisis in nuclear physics. Radioactive atoms undergoing a process called beta decay were shedding energy that didn't add up. Electrons flew out of the nucleus, carrying less energy than the book said they should, and the missing energy simply vanished, which is not a thing energy is supposed to do. Pauli's fix was to propose an invisible, chargeless, essentially massless particle riding out alongside the electron, quietly carrying off the difference. He wrote a letter to a group of fellow physicists, opening it with the line, "Dear radioactive ladies and gentlemen," and proposed his invisible fix, which he initially called a neutron, years before that name got taken by an actual, much heavier particle discovered in 1932. Enrico Fermi later renamed Pauli's phantom the neutrino, Italian for little neutral one. Pauli himself was not proud of it. He later admitted, in a remark historians still repeat, that he regretted inventing a particle nobody would ever be able to catch, and by his own math, he wasn't wrong to worry. He calculated his invisible particle could pass through 10 centimeters of solid lead without incident. Later physicists realized the real figure was closer to several light years of solid lead before you'd expect it to interact even once. Pauli reportedly bet a case of champagne that nobody would ever detect it. He lost that bet 26 years later, though barely, and only because two American physicists, Clyde Cowan and Frederick Raines, refused to accept undetectable as a final answer. Their first serious idea, floated in the early 1950s, was to build a detector and lower it near an actual hydrogen bomb test, since a nuclear explosion would produce a flood of neutrinos briefly rivaling a small star. They were talked out of this by a supervisor at Los Alamos, who pointed out, reasonably, that a newly commissioned nuclear reactor would produce a similarly enormous, far less suicidal flux of the same particles, continuously, for free. Cowan and Raines built a preliminary detector they nicknamed Herr Auge, German for Mr. Eye, and ran it at the Hanford site in Washington State in 1953. It wasn't conclusive enough, so in 1956 they rebuilt the entire experiment and installed it at the Savannah River plant in South Carolina, positioned 11 meters from an active reactor core and 12 meters underground, layered specifically to block cosmic ray interference. They called the whole effort Project Poltergeist, a nod to the neutrino's ghostly refusal to interact with anything. Inside 2 water tanks laced with cadmium chloride, sandwiched between 3 tanks of liquid scintillator, they waited for a very specific double flash of light. First, a prompt burst as a neutrino occasionally struck a proton and produced a positron. Then, a few millionths of a second later, a second burst as the resulting neutron got captured by a nearby cadmium nucleus. Any single flash could be faked by cosmic rays or background radiation. That 2-flash pattern, in that specific order, at that specific delay, essentially couldn't be faked by anything else. After 1,371 hours of data collection, they had it. The coincidence rate rose exactly the way it should when the reactor was on, and dropped exactly the way it should when the reactor was off. Reines eventually won a Nobel Prize for the work in 1995, 39 years after the fact, in part because Cowan had already died, and Nobel Prizes cannot be awarded posthumously. So, by the late 1950s, the particle Pauli was sure could never be seen had, in fact, been seen, using a reactor as an artificial source parked just meters from the detector. The much harder problem, one that would take another 45 years to fully resolve, was catching neutrinos that hadn't been custom delivered from a few meters away, but had instead traveled 93 million miles from the center of the Sun. In 1965, a chemist named Ray Davis, working with theoretical physicist John Bacall, built something audacious, 1,478 meters underground in the Homestake Gold Mine in South Dakota. A 380,000-liter tank of ordinary dry cleaning fluid, chosen because its chlorine atoms will, very occasionally, absorb a solar neutrino and transform into a radioactive form of argon that can later be extracted and individually counted. Bacall calculated exactly how many solar neutrinos should be striking that tank continuously, based on the best available model of how the Sun actually generates its energy. Davis ran the experiment for 3 decades, periodically purging the fluid with helium gas to pull out the accumulated argon atoms, sometimes finding only a few dozen after months of exposure to a genuinely staggering flood of incoming neutrinos. And what he consistently found was only about 1/3 of what Bacall's model predicted. Not 0, 1/3, again and again, for 30 years. This became known, dryly, as the solar neutrino problem, and for 3 decades it split the physics community roughly in half. Some insisted the Sun's model must be wrong. Others insisted Davis's chemistry must be flawed. A handful, including physicist Bruno Pontecorvo, floated a stranger idea, that the neutrinos leaving the Sun as one type were somehow turning into a different type on the way here, becoming invisible to a detector tuned to catch only the original flavor. For years, that explanation sounded like an excuse in search of new physics rather than an actual answer. It took until 2001 for anyone to prove it. The Sudbury Neutrino Observatory, buried more than 2 kilometers underground in a nickel mine in Ontario, was built specifically to solve this, using 1,000 tons of heavy water that could detect not just the electron-flavored neutrinos Davis's chlorine tank was sensitive to, but all 3 known flavors combined: electron, muon, and tau. When the total across all 3 flavors was tallied, the number matched Bacall's original solar model almost exactly. Davis hadn't been wrong. Bacall hadn't been wrong. The Sun really was producing exactly as many neutrinos as predicted. 2/3 of them were simply switching identities mid-flight, a genuinely strange quantum phenomenon called neutrino oscillation, which incidentally proves neutrinos must carry a tiny sliver of mass, something the original standard model of particle physics had assumed was exactly 0. Davis shared a Nobel Prize in 2002 for the original detection. Takaaki Kajita and Arthur MacDonald, leaders of the Super Kamiokande and Sudbury experiments respectively, shared another Nobel Prize in 2015, specifically for nailing down the oscillation itself. It had taken 69 years, from Pauli's letter to that final Nobel, just to confirm that the particle existed, behaved exactly as strangely as suspected, and could, with enough patience and enough tonnage of detector, actually be counted. The atmospheric half of that same 2015 Nobel Prize came from a different, equally strange piece of evidence, gathered a few years earlier at the Super Kamiokande detector in Japan. A 50,000-ton tank of ultra-pure water sitting a kilometer underground, watching for neutrinos produced when ordinary cosmic rays slam into the upper atmosphere. These atmospheric neutrinos arrive at the detector from every direction, some straight down, having traveled only a few dozen kilometers from directly overhead, and some straight up, having traveled clear through the entire diameter of the Earth, roughly 13,000 kilometers, before reaching the same tank from below. In 1998, the Super Kamiokande collaboration reported that the upward-traveling muon neutrinos, the ones that had spent far longer in flight, were consistently missing compared to the downward-traveling ones, in a pattern that depended precisely on how far each individual neutrino had actually traveled. That distance-dependent disappearance was the first clean, direct evidence that oscillation was a real, continuous, physical process happening to real particles in real time, not just a mathematical patch invented to rescue an embarrassing solar model. Notice what's buried in that entire 69-year story. Every single breakthrough came from making the detector bigger, not sharper. Not more sensitive electronics. Not a smaller, cleverer sensor. More tons of chlorine. More tons of heavy water. More liters of scintillator. That's not a coincidence, and it's not a matter of engineering taste. It's forced on you by the actual physics of how weakly a neutrino interacts with matter. Here's the actual number behind that weakness, because it's more useful than just saying weak. The likelihood of a neutrino interacting with any given atomic nucleus is governed by something physicists call a cross-section. And for the energies flowing out of the sun, that cross-section is almost unimaginably tiny. Something on the order of 10 to the negative 44 square centimeters per nucleus. To make that number mean anything, it's roughly as if you were trying to hit a single, specific proton with a thrown dart, except you were throwing that dart from somewhere outside the observable universe. If a particle refuses to interact at that level, making your detector's electronics faster or your sensors more light-sensitive doesn't help, because sensitivity only matters once something has already happened for a sensor to notice. The actual problem is that, statistically, almost nothing is happening anywhere near your detector, ever. There's exactly one variable in physics that fixes that. How much matter you put directly in the neutrino's path. Not how good that matter is, how much of it there is. That's the entire principle underneath every machine in this story, from a 615-ton tank of dry cleaning fluid in a South Dakota gold mine to the newest ones sitting under an entire ocean and an entire ice sheet. Which brings us back to the Mediterranean. KM3net, the deep-sea telescope off the coast of Sicily, is being built to eventually occupy an entire cubic kilometer of seawater, something like 1 billion tons of ocean, turned into a single instrument. Strings, called detection units, each nearly 700 meters long, hang from anchors bolted to the seafloor and are held taut by buoys near the top. Along each string are 18 glass spheres called digital optical modules, and packed inside each sphere are 31 separate light sensors, arranged around the glass to catch photons arriving from almost any angle. Getting a single one of these strings into place is its own small feat of engineering. Before deployment, the entire 700-meter string is coiled tightly around a reusable 2-meter spherical frame called a launcher vehicle, small enough to be lowered from a specialized ship-holding position over the target spot to within about a meter of accuracy. A remotely operated submarine connects the string's base to the seafloor cabling network, and only then does an acoustic signal release the launcher, which floats slowly back toward the surface on its own buoyancy, unspooling the entire string vertically behind it as it rises, before the now empty frame is recovered at the surface and reused on the next string. None of these spheres are looking for the neutrino itself. You cannot see a neutrino, full stop, with any instrument ever built, for the same reason a bullet already lodged deep inside a wall is invisible to a metal detector waved from across the room. What the spheres are watching for is the extremely rare aftermath of a neutrino accidentally striking a proton in the nearby water, an event so unlikely that even inside a cubic kilometer of ocean, most days produce nothing worth recording at all. Here's what makes that aftermath detectable in the first place, and it depends on a rule most of us learn slightly wrong in school. You're taught that nothing outruns light. That's true, but only in a vacuum. Light slows down considerably once it enters a dense medium like water or ice, losing something like 1/4 of its vacuum speed. A charged particle, produced the instant a neutrino slams into a proton, can still be moving close to its full vacuum speed as it shoots through that same water. Which means that, for a few billionths of a second, you get a particle genuinely outrunning light inside the very medium it's traveling through. When that happens, the particle sheds a cone of pale blue light behind it, in exactly the same geometric way a supersonic jet outruns sound and trails a cone-shaped sonic boom. That blue flash, called Cherenkov radiation after the Soviet physicist Pavel Cherenkov, who characterized it in the 1930s and shared a Nobel Prize for it in 1958, is the one and only thing those 31 light sensors in each sphere are built to see. Every design choice in this machine, the depth, the darkness, the spacing between strings, exists to make that single, split-second blue flash visible against a nearly black ocean. None of this explains why you'd sink the thing 3.5 kilometers underwater instead of building it in a large tank in a lab basement, the way Cowan and Raines built theirs. The answer is contamination. Cosmic rays constantly shower down through Earth's atmosphere, and their debris reaches the surface and shallow water in overwhelming numbers, drowning out the rare flashes scientists actually want. Bioluminescent organisms glow on their own in the deep sea, adding more noise. Even the ordinary radioactivity of potassium-40, decaying quietly inside seawater itself, produces a steady background hum of extra light. 3.5 kilometers of rock and water above the detector blocks almost all of that clutter while doing almost nothing to stop a neutrino, because a neutrino barely notices 3.5 kilometers of anything. That asymmetry. Everything else gets filtered out while the one particle you actually want sails straight through, is the entire reason this kind of astronomy works, and it's why the finished instrument won't function like a telescope pointed up at the sky. It functions like a telescope pointed down, using the whole planet as a filter, watching for neutrinos that have already punched straight through the Earth from the opposite side and are rising up through the detector from below. The same logic, at a different scale, is why there's a second version of this machine sitting under the ice at the South Pole. IceCube has been fully operational since 2010, using more than 5,000 optical sensors frozen into roughly 1 billion tons of some of the clearest, oldest ice on the planet, at depths between about 1.5 and 2.5 kilometers. Ice so free of bubbles and dust that light can travel through it in nearly straight lines for over 100 meters. Building it required melting boreholes into solid Antarctic ice with pressurized hot water, lowering a string of sensors into each shaft before the meltwater refroze solid around it, permanently locking each sphere in place, unlike KM3net's cables, which stay tethered to the surface and can, in principle, be hauled back up and repaired. IceCube and KM3net are pointed at the same underlying target for the same underlying reason, but each specializes in a different patch of sky, because each is using the Earth itself as a lens, and the Earth only gets in the way of certain directions at certain times of day. Here's where the misconception about sensitivity gets attacked from a completely different angle. Because volume over precision isn't just an engineering footnote. It's the reason this entire field is barely a few decades old instead of a century old. And there's one specific night in February 1987 that proves it better than any other. A star roughly 168,000 light-years away, inside a small satellite galaxy of our own Milky Way called the Large Magellanic Cloud, ran out of nuclear fuel and collapsed. In the span of about 10 seconds, its core imploded into a neutron star, releasing more raw energy, nearly all of it as neutrinos, than our own sun will produce as light across its entire 10 billion-year lifetime. Only a tiny sliver of that energy came out as visible light, gamma rays, and everything else combined. And even that sliver took a few extra hours to physically fight its way out through the star's own collapsing bulk before the explosion became visible to telescopes on Earth. 3 separate underground detectors, Kamiokande-e in Japan, the Irvine, Michigan Brookhaven detector in an Ohio salt mine, and the Baksan Neutrino Observatory in the Russian Caucasus, all originally built to search for something else entirely, called proton decay, happened to register a sudden, brief spike of neutrinos arriving from that direction in the sky about 2 to 3 hours before any telescope on Earth saw so much as a flicker of light. 24 particles, total, across all 3 instruments combined, inside a window of about 13 seconds. 24, out of a flood so enormous that, by the physics, something on the order of 10 to the 58th neutrinos were actually produced by that single collapsing star. The detectors that caught those 24 particles were genuinely sensitive, state-of-the-art instruments for their era. They still missed almost the entire flood, catching only the barest, luckiest fraction of stragglers, because none of them had anywhere near enough volume to catch more than a handful of particles from what was, by any honest description, a fire hose aimed directly at Earth. That's the exact lesson KM3net and IceCube exist to correct. You don't out-engineer a weak interaction with precision. You out-volume it. It took until 2010, and then the early 2020s, for anyone to build something with enough raw water or ice packed into it to move past counting individual stragglers from the nearest, loudest possible event and start doing actual astronomy on quieter, more distant ones. And the astronomy that resulted is the part that should genuinely unsettle the old assumption that better instruments always mean smaller ones. Because it turns out neutrinos are just one of 4 completely different ways the universe sends us information, and comparing the 4 exposes exactly what a planet-sized eye is actually good for. For most of the history of astronomy, seeing the universe has meant catching light. Not just the visible kind, but radio waves, infrared, X-rays, gamma rays, all of it made of photons. Light is extraordinarily useful and comes with a specific, built-in failure. It gets absorbed by dust and gas, which means the interior of the densest, most violent places in the universe can stay permanently hidden from any telescope, no matter how large its mirror. Then there are cosmic rays, mostly high-energy protons and heavier atomic nuclei, constantly raining onto Earth's atmosphere from deep space. Cosmic rays carry real information about what accelerated them, but they carry an electric charge, and the galaxy is threaded with weak magnetic fields that bend a charged particle's path over millions of light-years of travel. By the time one reaches a detector on Earth, its direction of arrival no longer points back to wherever it actually started. The information about its source gets scrambled out of it along the way. Then there are gravitational waves, ripples in space-time itself, which facilities like LIGO and Virgo have been directly catching since 2015. Gravitational waves travel in a straight line and are essentially never blocked by anything, solving the direction problem cosmic rays can't solve. But they carry almost no information about composition. They can tell you, with exquisite precision, that 2 extremely massive objects spiraled into each other at a specific moment, but almost nothing about what those objects were actually made of or what happened to the material around them afterward. That last limitation isn't theoretical. On August 17, 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars spiraling into each other roughly 130 million light-years away in a galaxy called NGC 4993. It was, and still is, the only confirmed neutron-star merger ever detected in gravitational waves, and within seconds a short gamma-ray burst arrived from the same direction, followed over the coming days by a genuine deluge of light. X-ray, ultraviolet, optical, infrared, and radio observatories worldwide all pointed at the same patch of sky and watched the same event unfold across almost the entire electromagnetic spectrum. It remains one of the most thoroughly observed single events in the history of astronomy. And yet, when the Antares, IceCube, and Pierre-Auger neutrino observatories searched the same direction, in a window 500 seconds around the merger and then again across the following 14 days, they found nothing. No neutrinos at any energy from Gev to Eve directionally associated with the event. That non-detection wasn't a failure of the instruments. It matched what physical models predicted for a jet observed from a wide viewing angle, off to the side rather than staring straight down its barrel. And it's actually a useful data point precisely because it's a null result. It tells you something specific about the geometry of that particular explosion that light and gravitational waves alone could not. So here's where the 4 messengers actually stand, side by side. Photons get blocked by dust. Cosmic rays lose their sense of direction. Gravitational waves keep their direction but lose almost all information about what actually happened. Neutrinos are the only one of the 4 that travels in a straight line, moves close to the speed of light, and carries direct, specific information about the nuclear interaction that produced it, all while passing through essentially everything in its path completely undisturbed. On paper, it's obviously the best messenger. The problem, the entire reason this only became usable astronomy in the last decade and a half, is that obviously the best messenger also happens to be the hardest one on the list to actually catch. The first time this paid off in a way that made headlines happened on September 22, 2017. IceCube registered a high-energy muon neutrino, an event cataloged as IceCube 170922A, carrying roughly 290 trillion electron volts of energy, with a computed 56.5% probability of being genuinely astrophysical rather than a background particle produced locally in Earth's own atmosphere. An automated alert went out to observatories worldwide within about a minute of the detection. NASA's Fermi Gamma Ray Space Telescope checked its records and found that a previously cataloged Blazar, TXS 0506+056, sitting at a redshift that places it something like 4 billion light-years away, was in the middle of one of the brightest gamma-ray flares it had shown in a decade of monitoring, and the direction matched the neutrino's arrival point almost exactly. The magic Cherenkov telescopes in the Canary Islands then made the first-ever detection of that specific Blazar at very high gamma-ray energies, confirming it as a genuine, active particle accelerator. A Blazar, for context, is a supermassive black hole feeding on surrounding gas and dust, firing a narrow jet of particles at close to the speed of light, aimed by pure geometric coincidence almost directly at Earth. The overall correlation between the neutrino and the gamma-ray flare was calculated at roughly a 3 sigma level of confidence, and when the IceCube team went back through 9.5 years of older, previously uncorrelated archival data, they found an entirely separate, independent excess of neutrinos from that exact same direction, clustered in late 2014 at a significance of 3.5 sigma, sitting in the data all along, unnoticed, before anyone knew to look there. What that single neutrino did, that light alone had never managed on its own in decades of watching that same Blazar, was settle a genuinely old argument. Physicists had suspected for years that blazars might be accelerating not just photons but actual high-energy cosmic rays, and light, no matter how energetic, couldn't distinguish this object accelerates photons from this object also accelerates protons to extreme energies. A neutrino, produced specifically when an accelerated proton collides with something nearby, is proof of the second claim in a way no photon could ever be, because photons don't require a proton collision to exist, and neutrinos, at these energies, essentially do. Then, in November 2022, IceCube did something arguably stranger. Sifting back through a decade of archived data, 2011 through 2020, and individually checking 110 known gamma-ray emitting objects, the collaboration found a startling excess of 79 neutrinos, give or take about 20, clustered on a single, much closer target, NGC 1068, also called Messier 77, an active galaxy sitting a mere 47 million light-years away, close enough that amateur astronomers can find it with a good pair of binoculars, at a statistical significance of 4.2 sigma. NGC 1068's core, though, is completely wrapped in a thick shroud of gas and dust, so dense that gamma rays at the energies you'd expect from an object producing that many neutrinos simply aren't detected coming out of it at all, by more than a full order of magnitude below where the neutrino flux implies they should be. Light, in other words, had been quietly lying to us about that galaxy for as long as we'd been pointing telescopes at it, not through any fault of any astronomer, but simply because photons cannot punch their way out through that much obscuring material. Neutrinos do not notice the dust at all. They walked straight out, the same way they walk straight through you, and told us what was actually happening in a place light had never been able to show us, confirming that a place producing high-energy neutrinos can be almost completely dark in gamma rays, which is exactly backward from what everyone studying blazars like TXS 0506+056 had come to expect. It's worth pausing here on the messenger neutrinos get directly compared against, because the contrast makes the entire argument sharper. On the night of October 15, 1991, a detector called Fly's Eye, an array of spherical mirrors staring into the dark Utah sky at Dugway Proving Ground, recorded a single cosmic ray with an estimated energy of 3.2 times 10 to the 20th electron volts, roughly 320 exa-electron volts. That's the kinetic energy of a thrown baseball, concentrated into one subatomic particle. It remains, more than 3 decades later, the most energetic single cosmic ray particle ever recorded on Earth, and physicists nicknamed it, without much subtlety, the oh my God particle. To this day, nobody knows what fired it, or from where, for a very specific reason. Even though Fly's eye recorded exactly where in the sky it came from, that direction is essentially useless information. A charged particle that energetic, crossing millions of light years of galactic and intergalactic magnetic fields on its way here, gets its trajectory bent and scrambled long before it ever reaches Earth's atmosphere. The arrival direction of a cosmic ray tells you almost nothing reliable about where it actually started. That is, the specific failure neutrinos were built to solve. And it's exactly why the story of the most energetic neutrino ever caught, the one this entire piece opened with, is so genuinely strange. Neutrinos aren't supposed to have this problem. They have no charge. Nothing bends them. Whatever direction one arrives from should be, in principle, the actual direction to its source. There's a second, related piece of physics worth knowing before we get back to that 2023 event, because it's one of the leading suspects in explaining it. In the 1960s, physicists Kenneth Greeson, Georgy Zatsepin, and Vadim Kuzmin independently realized that ultra-high-energy cosmic ray protons traveling across truly enormous intergalactic distances have to plow through the cosmic microwave background, the faint afterglow radiation left over from the Big Bang and filling literally all of space. Above an energy of roughly 5 times 10 to the 19th electron volts, a proton is moving fast enough that, from its own point of view, those ordinary background photons look energetic enough to trigger particle production, and the proton loses energy in the process, repeatedly, over cosmological distances. This predicts a sharp cutoff in the cosmic ray spectrum at that energy, now called the GZK cutoff, later confirmed by several independent detector arrays. Here's the useful part. That exact same interaction, a proton slamming into a cosmic microwave background photon, doesn't just sap the proton's energy. It also produces a predictable, calculable flux of neutrinos as a byproduct, called cosmogenic neutrinos, essentially fossil evidence of ultra-high-energy cosmic rays losing a fight with the leftover light from the birth of the universe. Which brings us back, finally, to that 220 PeV neutrino from February 2023, the most energetic one ever caught, officially designated KM3230213A. 2 years of careful analysis, published in Nature in February 2025, confirmed it as a real, extremely high-energy muon crossing the entire ARCA detector, triggering more than a third of the operating sensors and saturating the ones closest to its path. And it has still not been traced to any confirmed source. Worse, the statistics around it are genuinely uncomfortable, in a way that should make you trust this story more, not less, precisely because it doesn't resolve cleanly. The detector that caught it was running with only 21 of its eventual roughly 230 planned strings installed, about a tenth of its final design, for a grand total of 287 days of actual data taking. Given that partial configuration, an event that energetic should only appear, on average, once every 70 years. It showed up in the first year. That's not impossible. Unlikely events happen early sometimes, purely by chance, and this specific case works out to what physicists call a 2.2 sigma upward statistical fluctuation, roughly consistent with the same 1 in 70 odds implied by the exposure time itself. But it also sits in direct tension with IceCube, an instrument that has been operating for far longer, watching a comparable amount of sky, and has never recorded a single event anywhere close to that energy. As things currently stand, there are essentially 3 live explanations, and researchers actively disagree about which one is correct. 1. KM3net simply got extraordinarily lucky, and this is a rare statistical upward fluctuation of an otherwise unremarkable, ordinary astrophysical flux. 2. It's a cosmogenic neutrino, a genuine fossil of an ultra-high-energy cosmic ray losing an argument with the cosmic microwave background somewhere across intergalactic space, in which case its arrival should eventually be joined by more like it, at a predictable, calculable rate, as the detector keeps running. 3. And this is the option that makes some physicists visibly uncomfortable. There is a source out there producing neutrinos more energetic and more frequently than any current astrophysical model predicts. Or there's a piece of the fundamental physics of how neutrinos interact at these extreme energies that nobody currently has correctly modeled. Nobody knows which of the 3 it is. That's not a cliffhanger inserted here for dramatic effect. That is the actual, current, unresolved state of a field that only exists because someone finally built an instrument with enough raw volume in it to see something the existing models simply did not predict. And the instrument is about to get considerably less alone. KM3net itself is still under construction, aiming eventually for that full cubic kilometer at its Arca site off Sicily, alongside a second, denser array called Orca, sitting 2,450 meters deep off the coast of Toulon, France, tuned to lower energies to study the neutrino's own oscillating identity rather than distant cosmic sources. In Siberia, the Baikal GVD detector is steadily growing beneath the frozen surface of Lake Baikal, the deepest freshwater lake on Earth, using a deployment method unlike either of its cousins. Each winter, once a solid meter of ice covers the lake, engineers walk directly out onto that ice, cut holes through it, and lower new strings of sensors straight down into water roughly 1,300 meters deep, using the frozen lake itself as a stable, walkable work platform that neither the open Mediterranean nor the Antarctic ice sheet can offer. Off the Pacific coast of Canada, an early-stage project called P1 is testing the seafloor for a future full-scale array. In the South China Sea, a proposed detector called Trident would push the same basic design even further. And back at the South Pole, IceCube Gen 2 is planned to begin construction around 2027, aiming to instrument roughly 8 cubic kilometers of ice, 8 times the current IceCube's volume, with about 10,000 optical sensors plus an additional buried radio antenna array spread across more than 400 square kilometers, specifically to catch the even rarer, even higher energy events at the EVE scale that current detectors can only barely glimpse. There's also a quieter, stranger echo of this same principle happening back at the very mine where this whole story started. The Homestake gold mine, where Ray Davis spent 30 years counting individual argon atoms in a tank of dry cleaning fluid, still exists, now renamed the Sanford Underground Research Facility, and it currently hosts 2 entirely different multi-ton experiments built on the identical logic. One is Lux Zeppelin, 7 tons of liquid xenon sitting almost a mile underground, built not to catch neutrinos at all, but to catch dark matter, the unidentified substance that makes up roughly 85% of all the matter in the universe, and that, if certain leading theories are correct, should be passing through every square centimeter of your body at a rate of something like 100,000 particles per second, just as invisibly as any neutrino, waiting for a target finally large enough to notice it. The other is the Far Detector of Dune, the deep underground neutrino experiment, currently under construction 1.5 miles beneath those same South Dakota hills, designed to catch an artificial beam of neutrinos fired 1,300 kilometers straight through the solid rock of the Earth's crust from Fermilab in Illinois, no tunnel required, arriving at a detector eventually filled with 40,000 tons of liquid argon kept at nearly 200 degrees below zero. Different particles, different open mysteries, the very same gold mine, and the very same one-sentence justification underneath every one of them. Every single one of these projects, on every continent and under every ocean this species has meaningful access to, is founded on the exact same principle Ray Davis discovered by accident in a South Dakota gold mine 60 years ago. You cannot out-engineer a weak interaction with precision. You can only out-volume it. And right now, humanity is in the middle of building the largest coordinated out-volume it project in its history, one that will eventually watch the entire sky in every direction, all at once, using nothing more exotic than very large amounts of very ordinary water and ice. Step back from the engineering for a second, because there's something larger sitting underneath all of it. Every neutrino this network has ever traced back to a real source. The Sun, the 1987 supernova, that one particular Blazar, that one particular obscured galaxy, was already being produced in exactly the same way for the entire history of those objects, long before any human being existed to notice. The Sun has been sending neutrinos through your body since before there was a U for them to pass through, 100 trillion of them a second, mostly harmlessly, for your entire life, and for every life that came before yours, back to the point the Sun first ignited roughly 4.5 billion years ago. The supernova that lit up the sky in February 1987 finished happening 168,000 years earlier, meaning its neutrinos left that dying star around the time anatomically modern humans were first appearing in Africa, and had been traveling toward Earth for the entirety of human history before 3 underground tanks, built to look for something else entirely, happened to be running on the one night they arrived. Even that record-breaking neutrino from February 2023, whatever ultimately produced it, almost certainly left its source thousands, millions, or conceivably billions of years before any human being existed to build anything capable of noticing it at all. The delay was never on the universe's schedule. It was only ever on ours. We are not discovering new events. We are finally building instruments large enough to notice events that were never hidden in the first place, just invisible to every sense and every instrument we'd built until extremely recently. The universe was never quiet. We were the ones who hadn't grown ears yet. So the next time someone describes a breakthrough instrument and you picture something small, sealed, and impossibly precise, a chip, a lens, a needle threading some invisible target, remember that the most sensitive astronomical instruments on Earth are, physically, mountain-sized volumes of ocean water and ancient ice, chosen specifically because they are enormous, aimed not at the sky but straight, through the entire planet, built on the correct premise that some of the universe's most violent and most important events don't require you to look harder. They require you to stop looking and start listening, with something finally large enough to hear what has been pouring through you this whole time, silently, by the 100 trillion, every single second of your life, and you never noticed even once.